Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we will talk about a new topic, namely the case of nonlinear oscillations, and we will be using our standard arguments of perturbation theory, namely the case of regular perturbation. Okay, so nonlinear oscillations and phase space. Okay, so the key concepts that we are trying to we touch upon in this topic of discussion is the underlying math, which is the perturbation theory, and we will talk about the phase space analysis. Remember, this is a small overlap with our previous SwayamPrabha course on nonlinear dynamics, where we also looked at the phase plane analysis, but this time we are going to talk about in the context of collisions and planetary motions and atoms and so on. So phase space analysis, we will touch upon the case of Poincare-Bendixson theorem, which is a very useful tool in 2D, and we will talk about limit cycles. Okay, so as I just mentioned, this is a brief, very minute overlap with one of our previously lectured course on nonlinear dynamics. Okay, so then so suppose we directly go into the case of nonlinear oscillations, right? So suppose our restoring force, suppose we have a spring connected to a box, and our restoring force S is such that S is equal to m omega square x plus m lambda x cube. M omega square x plus m lambda x cube. So S is m omega square x, and where x is very, very small. So remember, when the deflections are small, we can essentially treat our restoring force to be linear. So this is the linear case of our remember, the general restoring force, we are taking it to be a nonlinear, right? And when we have small deflections, we see that the restoring force can be approximated by a linear by the linear term itself. Okay, so then what have we got here is so the restoring force. So in this case, we see that if we were to plot for this force, we were to plot the potential V of x, then the potential has the following figure. We see that the potential V, namely we integrate. So this is my force, we integrate S to get my potential V of x, and we see that this is equal to half m omega square x square plus 1/4 m omega x to the power 4, right? So this is the integral of x, and we see that this is a biquadratic potential, and we see that this is from minus a to a, and we have E, and of course we expect the potential maximum to be V max. So we see that if the system is within this well, it is going to oscillate, and if it is too far away, or if it goes beyond this well, it is not going to oscillate, which means that if the deflection is small, then the spring is going to oscillate, which means we are in the linear regime. And if the deflection is large, then we are in the non-linear regime. Then no longer the spring is going to show oscillations, it is going to be permanently altered, right? And we expect the position not going back to its original position for large deflection because of the non-linearity. Okay, so then we have few more terms here for the nonlinear term. It turns out that if lambda, the nonlinear coefficient lambda, is less than 0, then the spring is a soft spring. It softens. It's a soft spring means the more you deflect, the tendency of the spring is to lengthen and go towards irreparable change of length. So the spring is soft, right? And if lambda is greater than 0, then the more you deflect the object connected with the spring, the harder the spring becomes to alter the shape. So the spring is hard, so it hardens, right? So so that is what the terms are. So then we can write down the total energy of the system. The total energy of the system is given by half mv square plus half m omega square x square plus lambda by 4 mx4 is E, right? So this is my total energy of the system. Remember, the potential energy plus the kinetic energy, right? So the potential energy plus the kinetic energy. So this is what we have. Okay, so then because the kinetic energy is always non-negative, we expect the potential energy to be bounded above by the total energy of the system. This is the standard argument that we have always put forth. And in this case, we expect that if lambda is, well, so then the idea is, so this is the total energy. So we want to solve for the motion of the spring. We want to write the force balance. Remember, this equation 1 is the energy balance. So the corresponding force balance is, we need to write the force balance. We differentiate E with respect to x and see what happens. So the rate of change of energy. So the energy balance, the force balance this time of the system is d2x by dt2 1 over omega square plus x plus epsilon x cube is 0, and where my epsilon this time is a square lambda by omega square. Remember, we have done a variable substitution such that my small x is a times capital X, and we have further divided throughout by omega square, and we see that this time we have done so that now my initial conditions are capital X at t equal to 0 is 1, and dx dt at t equal to 0 is 0, right? Okay, so here we are. So what have we got? So now for epsilon, remember, we have set up this equation for this force balance in such a way that we are now ready to solve this equation or this force balance using our standard perturbation techniques, right? Now notice that the epsilon, we are going to treat epsilon to be our small parameter in our perturbative solution. And it turns out that since epsilon is a small parameter and epsilon is not with the term containing the highest order derivative, which means that the perturbation that we have to consider is the regular perturbation. This is a very crucial difference between singular perturbation and regular perturbation. If epsilon had epsilon been sitting here, then we would have to consider the case of singular perturbation, because taking epsilon equal to 0 is going to completely alter the form of the solution, because in that case epsilon was sitting with the term containing the highest order derivative. Here epsilon is not. So this is the case of regular perturbation, right? So then we can choose our solution x to be x at t comma epsilon, right? So for epsilon equal to 0, our solution reduces to linear system. Our solution reduces to linear system, and for epsilon much less than 1, our solution now can be, remember, for epsilon equal to 0, this is the simple harmonic motion, and for epsilon much less than 1, we are going to use regular perturbation method, right? Okay, so then I've just mentioned when to use regular perturbation, so I'm not writing that statement. I'm going to directly start expressing the form of the solution in regular perturbation. So what we have is, assume that my solution x of t comma epsilon is of the form x0 of t plus epsilon x1 of t plus epsilon square x2 of t, and so on. Why? Because we are using a power series. We are using a power series solution which is of the form for regular perturbation. The power series solution is bound to work for a regular perturbative setup, right? Now the problem is the following. We expect that it is quite possible, this form of power series is fine, we are going to get a solution, but it is quite possible that some of the properties, the individual properties of these unknown functions, are such that they do not satisfy the property of the final solution. For example, we may have that x of t comma epsilon is periodic and bounded. X of t comma epsilon is periodic and bounded, while xi of t are unbounded, and they are non-periodic. They are unbounded and non-periodic, right? So x of t comma epsilon is bounded, and this is very much the possibility. The problem here is that we have to do one more special treatment so that the properties of the perturbative solutions xi's and the final solution x, they match, right? We can assume some period of these unknowns xi's, right? So but how to find such a period is not known a priori. So what I'm saying is the following. We can it is not clear how to find the period tau of the series, right? I'm just taking the case of a bounded and periodic solution x of t comma epsilon. Now, so the idea is, in order to match these properties, let's say periodicity, the idea is we are going to now replace the time variable t, by a new variable s, which involves the angular frequency information, right? So I'm going to replace t by s such that x of s comma epsilon has a period 2 pi in s, whatever be the value of epsilon, right? We replace t by s such that the period 2 pi in s, whatever be the value of epsilon, right? Now the way we do it is, So that every term in the such that every term xi of t is periodic, right? This idea of replacing one independent variable by the other, which contains the time period information, is the so-called Lindstedt method. Lindstedt's method, right? Lindstedt's method. Okay. So what have we got is that we can assume that our angular frequency omega of epsilon is 2 pi by tau of epsilon, right? And this is my angular frequency of the solution. The angular frequency of the solution of x of s comma epsilon, right? And now I'm going to use this information and see what happens. So now if we use this information, we see that what have we got? So my new variable s is omega times t. So now I have to differentiate not with respect to t in my new equation, but with respect to s. So my let me say my original equation was a, and from a I see that my new equation is omega by capital Omega square x double prime plus x plus epsilon x cube is equal to 0. So this is my a prime, right? And here my initial condition is x equal to 0. Sorry, at t equal to 0, x is 1, x prime is 0, and this is at s equal to 0. Okay. And then we can expand omega. Now omega is also an unknown of the system. Remember, omega is a function of epsilon, so it's an unknown function, and we have introduced a new variable omega as well. So we want to again use, what tool we have? We have the tool of perturbation. So again, to find omega, we use the perturbation form, that is the power series, right? So we can assume that omega epsilon by capital Omega is 1 plus omega epsilon, omega 1 plus omega 2 epsilon square, and so on. So we have again used a power series. So let me call this equation as B, right? And now I am going to plug this from A prime and B. So I'm going to plug the power series information of omega into A prime, and I see that I see all this. I plug this series information, and I see the following. Well, I also have the initial condition here. Initial condition to see that we have the following. The equation reduces to the following form. So 1 plus omega 1 epsilon plus omega 2 epsilon square plus and so on times x naught double prime plus epsilon x1 double prime plus epsilon x2 double prime and so on, and plus x naught plus epsilon x1 and so on, and then there is a third term epsilon x cube, so plus epsilon x naught plus epsilon x1 plus epsilon square and so on. This is to the power 3 is equal to 0. So then we need to solve this setup. Well, there is also the initial condition. The initial condition here is, from here we get that this is x naught plus epsilon x1 plus epsilon square x2 and so on. This is equal to 1 because x is equal to 1. And similarly, x naught prime plus epsilon x1 prime plus and so on. This is equal to 0 because x prime is 0. So these are the two initial conditions which are expanded in the power series. And from here, I can start to equate the order epsilon terms, the order epsilon to the power 0, epsilon to the power 1, epsilon to the power 2, and so on. So when we do that, so order epsilon to the power 0 term, we see that this is x naught prime plus x naught is 0. So this is the leading order. This is when x naught is equal to 1 and x naught prime is equal to 0 when s is equal to 0. So leading order term. And then epsilon to the power 1 order term is x1 double prime plus x1 is equal to minus 2 omega 1 x naught double prime minus x naught's cube, right? And we get that this is also equal to, we can plug in, we can solve this first equation. We can see that the first equation gives us x naught is equal to cos of s, and that satisfies these two initial condition, right? And we can plug this information here in the second equation, and we see that this is also equal to 1/4 this is also equal to 1/4 time 8 omega 1 minus 3 cos s plus 1/4 cos 3s, right? Remember, we want periodic solutions. We want x size, x0 is periodic because it's cos s. We want x1 also to be periodic, so we take this term equal to 0, and that gives us the fact that omega 1 is 3/8 because this quantity is not periodic. It's not periodic in omega. If we take this quantity is periodic, so the final solution will have a periodic term plus the forcing term, and we take one forcing term to be 0 so that the periodicity is retained. So then we can solve this equation to find that x1 is 1/32 times cos of s minus cos of 3s, and that is the solution up to first order of epsilon. So we can write my solution x of s comma epsilon to be x naught plus epsilon x1 plus order epsilon square. I am not writing the higher order term. So this is x naught is cos s plus epsilon by 32 times this quantity here plus order epsilon square, right? And what we see here is so this is the equation that we have got, and my omega, the angular frequency now is omega 0 plus epsilon omega 1 plus order epsilon square. Remember, omega by capital omega was 1 plus epsilon omega 1 and so on. So this we have found out to be equal to 1 plus 3/8 epsilon plus order epsilon square, right? And from here I can see that epsilon is a lambda by omega square, which is much less than 1. So epsilon comes out to be a lambda by omega square, which is much less than 1. And from here, this is the parameter. This is a small parameter that we have worked with, right? So all these final solutions are valid only for this condition, and we see that my period tau is 2 pi by omega, which is roughly equal to 2 pi by capital omega. I am using this formula for angular velocity here, this formula. So this is 1 minus 3/8 epsilon plus order epsilon square. Okay, and that's it. I think so my solution is here, my period is here, the period of the system, and we can see that as we continue to increase continue to add order epsilon terms, the period is going to continue to get modified, but at least the most important property is at least the solution as a whole is periodic. So that is how we try and approach using regular perturbation. We try and approach in order to find the solution of these complicated non-linear systems. So now in the next module we will talk about a very specific form of the system, namely the so-called autonomous system. And we will show some very interesting results for autonomous systems, namely the so-called Poincare-Bendixson theorem. So let me wrap up by just mentioning what is there in the next module, namely the case of autonomous system. So thank you very much, and thank you so far for listening. Thanks a lot.